You've been there. It's 2 a.m. Something is buzzing near your ear. You slap yourself in the face. You miss. The mosquito does not. Now imagine that mosquito, that smug, aerodynamic little nightmare, is the small one. Here's a question that sounds like it belongs in a bad sci-fi pitch meeting, but is, in fact, grounded in serious paleobiology. What would happen if Earth's oxygen levels doubled overnight? The answer isn't just things get weirder. The answer is that insects, every ant, every dragonfly, every mantis currently minding its business in your garden, would begin a transformation that would fundamentally restructure the food chain. And spoiler, we are not at the top of the new one. But to understand why oxygen is the single dial controlling insect size, we need to talk about why bugs aren't already the size of golden retrievers. Because the reason is more interesting than you'd expect, and it has everything to do with a breathing system so passive, it's almost embarrassing. Here's something insects never brag about. They don't have lungs. Instead, they breathe through a network of tiny surface pores called spiracles, little holes along their bodies that allow oxygen to passively diffuse inward through tubes called tracheae. No pumping, no active respiration, just drift. Oxygen wanders in, carbon dioxide wanders out, everyone goes home. This works beautifully when you're small. When the distance between your skin and your core organs is measured in millimeters, passive diffusion is fast enough, efficient, elegant even. But here's where the square cube law ruins everything. When you scale up an object, say an ant, its volume increases far faster than its surface area. Double the length, you get 8 times the mass, but only 4 times the surface. That means as an insect grows, the ratio of oxygen-absorbing surface to oxygen-hungry tissue gets worse and worse. Past a certain size threshold, oxygen simply cannot diffuse fast enough to reach the insect's core. The insects suffocate from the inside, while technically breathing. This is the oxygen ceiling, the hard biological cap on arthropod size in a 21% oxygen atmosphere. And it's the reason the largest insects alive today top out around 6 inches, rather than, say, blocking your driveway. But here's the thing, this ceiling is not fixed. It is directly proportional to ambient oxygen concentration. Raise the oxygen, raise the ceiling. It's almost that simple. And we know this because it has moved before. About 300 million years ago, the ceiling was much, much higher. The creatures that lived under it were things you would not want to meet in a dark Carboniferous forest, which means this isn't speculation. It's a rerun, and reruns, as anyone who's watched enough nature documentaries knows, are rarely less dramatic the second time. Let's set the scene. Atmospheric oxygen climbs from 21% to somewhere between 30 and 35%, the levels that define the Carboniferous period, roughly 300 to 350 million years ago. Within a geological eye blink, insects, which reproduce in enormous numbers and evolve with terrifying speed, begin to fill the new space available to them. First comes the metabolic surge. More oxygen means more fuel for cellular respiration. Insects become faster, reaction times sharpen, musculature strengthens. An already efficient predatory system becomes something closer to a precision instrument. Think of it like upgrading from regular gasoline to rocket fuel, except the car also grows legs and starts making decisions. Then comes the part nobody talks about, molting. All insects periodically shed their exoskeletons to grow. It's already one of the most metabolically expensive things an animal can do. Now imagine doing that when your exoskeleton is the size of a car door. The energy demand would be extraordinary. The insect is temporarily soft, vulnerable, and pumping every available resource into rapid hardening. For a brief window, it is as close to helpless as something terrifying can get. The selective pressure here would be intense. Only the fastest molters, the most metabolically efficient ones, survive. The slow ones get eaten. Evolution doesn't take requests. It just bills you for the upgrade and moves on. And what's the result? Insects that are not just bigger, but better, more efficient, more aggressive, optimized by pressure we can barely imagine. Suddenly, a can of Raid isn't a pesticide. It's a mild deodorant for the thing living in your garage. Allow me to introduce your new overlord, dragonfly. During the Carboniferous period, a genus called Meganeura had a wingspan of up to 28 inches. In a reoxygenated world, we're talking wingspans approaching 2 to 3 feet, bodies the length of your arm, and flight dynamic that would make aerospace engineers mildly depressed. Here's what makes this particularly unsettling. Dragonflies are already the most effective aerial hunters on Earth, with a kill rate above 95%, higher than lions, higher than great white sharks. They don't chase prey. They calculate intercept trajectories in real time using some of the most sophisticated visual processing in the insect world. They are, by any honest metric, better at hunting than we are at almost anything. Scale that up. Give it a 2-foot wingspan and a body hardened by a 35% oxygen atmosphere. It is no longer a dragonfly you're watching from a comfortable distance. You are the prey item it has already calculated a path to. Then there are the ants. A single ant is irrelevant. A colony of 10 million ants with bodies the size of a small dog is not an insect problem. It is a logistics problem, a military problem, and a theology problem all at once. Ant colonies already demonstrate collective behavior that solves complex challenges: routing, load distribution, environmental modification, agriculture, warfare. They farm fungus. They take slaves. They build climate-controlled superstructure. They already do all of this at thumbnail scale. Scaled up, an ant column wouldn't just be something you step around on the sidewalk. It would be something you evacuate cities for. And the mantis. The praying mantis strikes in under 50 milliseconds, faster than a human can consciously register movement, let alone respond to it. At current scale, this is alarming trivia. At 4 feet tall, with forelegs reinforced by an exoskeleton built for a richer atmosphere. This is a creature operating entirely outside the window of human reaction time. The mantis doesn't chase. It doesn't need to. It waits, perfectly still, and then it isn't waiting anymore. The mantis is already a perfect predator. Doubling oxygen doesn't fix something broken. It supercharges something that was already working exactly as intended. Here's where it stops being a fun thought experiment and starts being genuinely uncomfortable. Every ecosystem is a network of interlocking dependency. Shift one relationship, and the pressure redistributes across the entire system. Invert the predator-prey dynamic between insects and vertebrates, and the entire web restructures from the bottom up. Birds and small mammals, currently the primary biological check on insect populations, would face immediate, severe pressure. Songbirds that eat beetles now face beetles eating songbirds. Frogs, lizards, and small rodents that currently sit comfortably above insects in the food chain would find that position renegotiated forcefully and without much notice. Humans, specifically, would be in a position that our entire evolutionary history has not prepared us for. We are not fast. We are not armored. We do not have venom or natural armor, or the kind of reaction times that would make us competitive in this new hierarchy. Our primary advantage, cognition and tool use, would redirect almost entirely toward a single objective: staying inside. Think pressurized habitats, sealed infrastructure, architecture designed not for aesthetics or comfort, but for exclusion. Every door a siege door, every window a vulnerability assessment. There's also the fire problem, and it is a significant. Higher atmospheric oxygen doesn't just affect biology. It affects combustion chemistry at a fundamental level. At 35% oxygen, the ignition threshold for organic material drops dramatically. Damp wood burns, green vegetation sustains flame. A single lightning strike in a forest wouldn't start a fire in the way we understand the term. It would trigger a cascading combustion event across hundreds of square miles. Wildfires in the Carboniferous period are believed to have been continent-scale events, evidenced by thick charcoal layers in the fossil record. In a modern, reoxygenated world, with current levels of biomass, fire management wouldn't be an environmental concern. It would be the central organizing challenge of human civilization. So to recap, giant insects, inverted food chain, and the entire surface of the planet is a fire hazard. Humanity adapts or becomes sediment. Here's where the scenario takes one final, interesting turn. Oxygen is not purely a gift. At elevated concentrations, it becomes chemically aggressive in ways that work against the very organisms benefiting from it. Oxygen molecules at high partial pressures strip electrons from cellular structures through a process called oxidative stress, generating free radicals, unstable particles that damage proteins, degrade lipids, and introduce errors into DNA replication. In a 35% oxygen world, every organism running a high metabolic rate, which describes every large, active, fast-growing insect in this scenario, would be accumulating cellular damage at an accelerated pace. They would grow fast. They would be powerful. They would also age quickly, degrade quickly, and die young by any biological standard we'd recognize. This creates something stranger than a world of permanent giant insects. It creates a world of rapid, compressed, relentless, evolutionary cycling. Short lifespans mean shorter generations. Shorter generations mean faster natural selection. Faster natural selection means these insects wouldn't just be large and dangerous now. They would be iterating towards something worse at a pace that makes our own 200,000 years of anatomical modernity look like a leisurely afternoon. They would be terrifying, short-lived, and constantly improving. A new dominant form every few thousand years, which is somehow more unsettling than if they just stayed large and stable. So here's where we land. A doubling of atmospheric oxygen wouldn't produce a monster movie. It would produce something more methodical than that. A slow, physics-driven reorganization of every biological hierarchy on the planet, fueled by a gas we currently take for granted with every breath. We know this isn't imagination because it already happened. The Carboniferous period is in the fossil record. The giant insects existed. Meganeura was real. The charcoal layers from those ancient wildfires are real. The conditions that produced all of it were real, measurable, and thoroughly documented. What keeps insects small today isn't some fortunate accident of evolution. It's a physical constraint, the oxygen ceiling, holding firm at 21%. And we live in the comfortable space beneath it, completely dependent on it, mostly unaware of it. So next time you trap a spider under a cup and carry it to the door, feeling generous, feeling patient, feeling like the reasonable adult in the situation, just remember, you're not being kind. You're just relieved it fits under the cup. Now here's your question for the comment. Which insect would be the most terrifying at 5 feet long? Mantis? Dragonfly? Wasp? Make your case below. I'll read the ones that keep me up at night.